Oftentimes in physics or mathematics, we are faced with a situation where solving a question by hand is no longer possible. A given problem might benefit from numerical investigation, which can also be tricky. One of the most powerful frameworks we have to investigate such problems are Monte Carlo algorithms, which rely on randomly sampling quantities that we're interested in. But there's a key word in here. That word is random. When you sit down and write your code, how does the computer generate random numbers? Well, of course, they aren't truly random. It generates pseudo-random values, which means the sequence of numbers generated approximate a sequence of random numbers. Probably the simplest way to do this yourself would be to implement a linear congruential generator, which is an algorithm that gives you back pseudo-random numbers using modular arithmetic. The generator works by defining the following recurrence relation, where here we call m the modulus, a the multiplier, and c the increment. And the first value x0 would be the seed. So let's look at a simple example of this in Python. Let's say we want to create uniform real numbers on the interval 0 to 1. So let's choose a is equal to 75, c is equal to 74, and m is equal to 2 to the power of 16 plus 1. Here we'll also take our initial seed to be x is equal to 4. I represent this in Python as the function LCG, where we pass a seed x0 and the total number of pseudo-random numbers that we want to generate. I choose to store the output in an array called p_nums, which I initially fill with all zeros. We then populate the array for our random numbers using the recurrence relation. Running this, you will see our variable pseudo_nums gives back a number of random integers. Next, we know that the largest number our pseudo-random number can take is 2 to the power of 16. So let's divide all of our integers by that number so that our new maximum is 1. Let's check to see if we get a uniform distribution. We will do this quick and easy by just doing a histogram with pyplot. Let's say we give it 10 bins. With 10 to the 4 numbers generated, we don't quite get a flat uniform distribution. But if we ramp this up to 10 to the 6, we definitely can't visually tell that we don't have a uniform distribution. Okay, so let's discuss why I chose these parameters, aside from the fact that it is how the old ZX81 generated random numbers. Perhaps an obvious thing to note is that we want our recurrence relation to have an extremely large period so that we don't repeat numbers. So the cool thing about these generators is that for certain choices of parameters, we know the period and can make it quite long. So let's assume that we set the increment c to 0 and have the modulus be a prime number. Then if the multiplier is a primitive element of the integers modulo m, the period is m minus 1. And of course, you should make sure your seed is set to be an odd number. Okay, so what about a case where the increment is non-zero? We can get a period equal to m if we choose our parameters correctly. We want m and c to be relatively prime. We want a minus 1 to be divisible by all prime factors of m, and a minus 1 is divisible by 4 if m is divisible by 4. These requirements are known as the Hall-Dobel theorem. So now that we have some requirements for a random number generator, let's explore a random number generator that was dubbed the most ill-conceived random number generator ever designed. This example will show us how, despite producing pseudo-random numbers, each generator should be properly vetted before use in a project. This random number generator was IBM's RANDU, which was used in the 60s and 70s and had the following recurrence relation. This will generate pseudo-random numbers, which are in fact uniformly distributed on the interval 1 to 2 to the power of 31 minus 1. Mapping to the open interval 0 to 1, we can use the following formula. So let's code up this random number generator in Python and try to understand why it doesn't work so well. First, let's check if it does in fact give us a uniform distribution. So using the skeleton code from before, we can create our RANDU algorithm and go through and create our histogram. At 10 to the 6 total random numbers, we can see that the RANDU algorithm seems significantly less flat than the first example did. So already perhaps this is concerning, but certainly not warranting complete skepticism. So let's do one more test to see what's actually happening, and we'll see something surprising. So let's plot a 3D grid of the following points: xj, xj plus 1, and xj plus 2. We will grab the first 10,000 points from RANDU that were generated to do this. Plotting these points in a 3D grid can be accomplished with the following code quite easily, where y1, y2, and y0 are the 3 coordinates. So running the plot, we see this blob. So nothing looks too suspicious, right? Well, rotating it, we shockingly see that all of these numbers are organized into planes in 3-dimensional space. Now, this isn't completely unexpected. We would always expect these points for an LCG to fall into some amount of parallel hyperplanes, but here we have an extremely small amount of planes. In this context, a good LCG should generate over 2,000 planes. RANDU only has a handful. To see this, let's look at our first LCG example in the same picture. So we have our y0, y1, and y2 from the pseudo underscore nums from the first example. This is accomplished with the following code here. Now, as we shift around, perhaps some planes become visible, but you can see that we fill the 3-dimensional space much more finely compared to the RANDU generator. If we try to uniformly sample a unit cube with RANDU, RANDU would only sample 15 parallel planes as we saw, which is absolutely abysmal compared to the over 2,000 planes that would be sampled by other LCGs. We can actually work out the equation of the planes quite easily for RANDU. First note that A can actually be written as 2 to the power of 16 plus 3. So then let's look at the j plus 2 term. We can use our recurrence relation to type out the xj term, and expanding this we get the following expression. So simplifying again, we see that the planes live in 3-dimensional space with the following expression. So RANDU is long gone in computational packages, and modern random number generators are much more reliable. But it's interesting to see the types of mistakes you can make if you aren't too careful. But that's it for today, everyone. I hope you liked the video. If you did, feel free to like, subscribe, and leave a comment below.